Hello everyone, this is video 16.4. We're going to be looking at using fraction arithmetic to calculate probabilities. So in the last video, 16.3, we looked at using the uniform probability model and drawing tree diagrams to find probabilities. So now that's a very concrete approach. So now we're going to look at a very abstracted approach. We're going to use fractions and actually do calculations to find these probabilities, so we don't have to draw a ton of tree diagrams, especially a ton of really big tree diagrams when we want to find a probability. So let's get started. So let's go back to the spinner from video 16.3. This is the same spinner that we saw in the previous video. And the problem that we were looking at was that we wanted to get a 1 on 2 consecutive spins. So we wanted to spin the spinner twice and have it come up 1 and then 1. Now, we solved that problem in 16.3. We did it by drawing the tree model using the uniform probability model. And so we had 5 different branches to start off with, and then each of those 5 branches had 5 branches coming off. And so we found that there was one branch that did what we wanted it to do. There was that one branch that went to the 1 and then to the second one. So there's one way that works out of 25 total. So we knew our probability was 25. You can probably see the shortcoming in this approach. If we were doing a problem with 3 spins, now we have 5 times 5 times 5. That's 125 branches we got to draw out. Or if this spinner had, say, 12 different sections, on 2 spins, that's 144 branches we got to draw. Not to say that you couldn't draw 125 or 144 branches, but your students are probably not going to want to sit still and watch you draw that many. Your board may not be big enough, and you just may have better things to do with your time than stand there and draw all these or prepare that ahead of time. So there has to be a better way to solve larger problems like that. And this needs to be part of the motivation in moving into fractions. The concrete model gives us a way to see what's going on, but eventually we need to abstract that into something that is a calculation. We don't want to go straight to the calculation without some sort of concrete foundation. We also don't want to start with the concrete foundation and just stay there, because it's a very unwieldy way to solve problems. So this transition from this concrete explicit model into the more abstracted implicit model is a big part of being an effective math teacher. So let's go back to 16.2, where we looked at multiplying things when we had multi-stage outcomes. And so the first problem we looked at had a die and a spinner, and so we were looking at how many possible outcomes we had for that. And so we saw there were 6 for the die, 4 for the spinner. So 6 times 4 gave us 24 different possibilities. And we can do the same thing here. If we look at how many ways can I get a 1 on that first spin, well, there's 1. And then if I look at how many ways can I get, where's my pen's not working. If we look at how many ways can I get a 1 on the second spin, that's a 1. And so 1 times 1 gives us one way total of getting that outcome. There we go. Get the pen working now. So one way on the first spin, one way on the second spin, and then we multiply those together to get one way total. If we look at the total number of possibilities, the total number of outcomes, then on the first spin we have 5 different outcomes. Again, not 3. There's 3 different values, but there's 5 different outcomes because that 2 occurs more than once. So we've got 5 different outcomes for the first spin, 5 different outcomes for the second spin. So that's 25 possible total outcomes, of which 1 satisfies our event. So 25 things can happen. One of them is what we want. We've constructed this using a model where everything is uniformly distributed. Everything has the same probability. So I know that the probability of getting a 1 and a 1 is 1/25. So that's what this 1, 1 here represents, that I want a 1 on the first spin and a 1 on the second spin. So we could use this idea from 16.2 of calculating the total number of outcomes for the event and for the sample space, and then we get the probability from there. But this is the same as if we had just done the probabilities and multiplied them together. If I look at the probability of getting a 1 on the first spin, that's 1/5. The probability of getting a 1 on the second spin is also 1/5. And so when I multiply 1/5 times 1/5, I get 1 times 1 over 5 times 5, and that's 1 over 25. Now, if you've been through 137 already, then multiplying fractions hopefully makes a little bit more sense. If you haven't been through 137 yet, and it's been a while since you multiplied fractions, then sort of like keep this in the back of your mind a little bit, and then when you go through 137, you'll learn more about ways of talking about and showing fraction multiplication. So I'm going to do this video under the sort of presumption that you've already done some stuff with fractions in the past. Like I said, if that's not the case, just kind of hang on to it, and then later on when you do take 137, hopefully you'll review this a little bit and it'll make some degree of sense. So the point is that in a lot of these cases that we're going to look at, and we'll look at some cases where they work, and we'll look at some cases where, or we'll look at a case where it doesn't necessarily work. We use multiplication to find the probability of multi-stage events. So we're going to use multiplication with these fractions to show how we can find these probabilities. And everything that you've learned about fractions, like I said, will apply to this understanding. So, for example, one of the models that we use to show fraction multiplication is this area model, this sort of grid model that we have here. And so you can see that what we've got here along the side is these are the outcomes for the first spin. So I'm just going to write first spin here, and so we get a 1, a 2, a 2, a 2, and a 3. And then along the top, we have the outcome for the second spin, 1, 2, 2, 2, 3. And so if we combine these together, you can see, for example, this 2 and this 3 meet up here at the ordered pair 2, 3. So we probably wouldn't hurt to put these in parentheses, but we'll just sort of make clear that the first number is the first spin and the second number is the second spin. Now, using this area model or this grid model, we can see that there are 25 different outcomes, of which one satisfies the condition that I'm looking for, the 1, 1. And so this area model allows us to see the fraction multiplication. The solution that we get should be 1 over 25. Keeping in mind all the same dangers and pitfalls using this model that we had with the tree diagram. A lot of students are going to want to make this area model a 3 by 3 and just do, we'll draw it down here real small. So a lot of students are just going to want to do 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, and see that there's only 9 possibilities. So if you're not clear on why this doesn't work, so let's put a big X through this so nobody gets confused, and let's put a frowny face over here. If you don't remember why the 3 by 3 doesn't work and why the 5 by 5 does work, you may want to go back and review those videos. We can make the 3 by 3 work if we put the probabilities in the grid, but the whole point of the grid is that it's explicit and proportional, so we sort of don't want to mix those two models together. That kind of makes things a little bit more confusing. So now that we've seen how we can use multiplication and these grid models to solve some of these probability problems, I want to look at a little bit larger of a problem and combine one more idea in with this. So we're playing a game with a fair coin, fair two-sided coin, and a fair die, six-sided die. So we win if we flip heads on the coin and roll a 5 or a 6 on the die. So what is the probability that we're going to win? And we're not going to think about the expected value part of this. We're not worried about how much we win, how much we lose, or anything like that. We just want to know what the probability of this event is going to be. So I want to go through this two different ways, and so we can see how the two ways are different and how they're similar, how they show the thinking in slightly different ways, and yet find the same solution. So the first way is this concrete way, the area model, this grid approach. So we can make our grid, and we can see that along the side we've got heads and tails, and then along the top we've got 1, 2, 3, 4, 5, 6. So here's our coin over here, and here's our die over here, our single die over here. And so we can see our ordered pairs: heads 1, heads 2, heads 3, so on, so on, so on. And if we look, we can see there's two sections that satisfy our event condition. There are two areas that have heads with a 5 or a 6. We know that this is uniformly distributed. The head and the tails both have equal probability, and the 1, 2, 3, 4, 5, 6 all have equal probability, so we know those are all uniformly distributed as well. So everything inside the grid is a uniform probability. Everything has the same probability, and there's 12 different things, so the probability must be 2/12, or if you want to reduce it to 1/6, you certainly can. A lot of problems like this, we don't reduce the fractions for reasons I'll show you here in a moment, but if you see a problem like this in a book and you see that they've left it as 2/12 and you're wondering why didn't they change it to 1/6, you'll see why in a moment. So this is one way of doing it, is our concrete approach, very explicit way of solving this probability problem. Now, solution 2 is using the fraction approach. So what I've done is I've broken this into two events. So there's two ways that we can win, and so I want to find these probabilities separately. So one way that I can win is that I flip heads and roll a 5. So the probability that I get heads and the probability they get a 5, we just learned I can multiply these two probabilities together, and so the probability of heads is 1/2. The probability of a 5 is 1/6. So I multiply those together and I get 1/12. For event 2, I want heads with a 6. So I've got probability of heads again is 1/2. The probability of 1/6 again is 1/6. So I get a probability here of 1/12. Now, this should sort of line up with what we just saw in the previous solution. So we know that this was one of the 12 sections, and this was one of the 12 sections. So everything should make sense, hopefully, so far. If we combine these together, I've got 1/12 and 1/12, and that should give me 2/12, which is the same thing we got in the previous solution. So generally, when we want the probability of x and y, we're going to multiply those two probabilities together. So for example, in order to win, I needed to get heads and a 5. And so that was why I multiplied the 1/2 by 1/6 to get 1/12. So when we have something where we need both things to occur at the same time, or as part of the same event, or as part of the same outcome, or part of the same condition, however you want to think about it, we need these things to happen and one and the other, then generally we're going to multiply these things together. There are some exceptions to some of this that we're not going to cover in this class. If you're curious about this, I mean, there's other courses you can certainly take that sort of address like when this is not going to be the case, and I'm not going to get into a whole lot of details on it. But so that's why I'm kind of hedging and saying generally this is the case. But for almost every case you're going to see in this class, it's going to be the case. So when I want one and another to happen, I'm going to multiply those. Now, when I want the probability of x or y, when x could happen or y could happen, then I'm going to add those together. So for the last part of that second solution that we did, I could win on a heads and a 5, or I could win on heads and 6. So once I found those two probabilities, So event 1 or event 2, and then I'm going to add those together, and that gave me my probability at the end of 2/12. So you might be wondering, well, when does this not work? So we'll take our coin and die game and we'll change the rules a little bit. Say we have the same game, but now we win if we flip heads or roll a 6. So if we look at this grid, we see that the probability of flipping heads, well, there's 6 ways that could occur. And so the probability there is 6/12. And the probability of rolling a 6, well, there's 2 ways that I would roll a 6, and that's 2/12. So if I add these together, I get 8/12. But if I count 1, 2, 3, 4, 5, 6, 7, there's only 7 winning outcomes. So what happened? How come we can't add in that case? And you can probably tell what happened, and I've made this a different color so you can kind of see it a little bit easier. What's happened is I've counted that heads with the 6 twice. I've counted it as part of the heads event and also as part of the 6 event. Now, I'm not telling you this because you're going to see a lot of problems like this in this class. I'm telling you this so you are aware that when you're coming up with problems like this, if you want to avoid this topic, you need to make sure that you sort of set conditions so that this doesn't happen. You want to make sure that these two events all sort of are separate from each other and they don't overlap. We could solve this by breaking it into much smaller events and then counting each one of these events. We could eventually break it into 7 events. But students would most likely take heads as one event, 6 as one event, and put them together in a way that doesn't work. How do you make this work computationally or algebraically? Again, that's sort of beyond the scope of this class, so we're not going to get into that now. But I just wanted to make you aware of when this doesn't work so you can create problems that work the way you want them to work, essentially. So for our checkpoint problem, the probability that this spinner is going to land on green both times if I spin it twice. So I'm going to spin this thing twice. I want to find the probability that it comes up green both times. And then as a little bit of a challenge problem, if I spin it 3 times, what's the probability of getting green 3 times? There's a lot of problems we come up with using the spinner. We could also do what's the probability that I get the same color both times. So not just green both times on 2 spins, but if I spin, essentially that I get doubles, that I get red with red, or I get yellow with yellow, or I get blue with blue, or I get green with green. So you can hear that or, so that should hopefully give you an idea of where to go with this problem. So I'll leave this problem with you. As always, if you have any questions about this problem or anything else in this video or the homework or the book or anything else involving this section or chapter 16, please bring your questions to class and we'll get them answered. All right, thanks.